Hello, everyone. Welcome to the next to last lecture of this semester. And to the last week of classes. So today we are going to have a very interesting lecture, and that will be on the TCP flow control and actually congestion control. And remember, here we are talking about the transport layer. So this is about the networking stack, the internet stack. And as you can see, the transport layer, and if you remember, sits on top of the network layer. And the transport layer, it's implemented actually is the first layer if you go from bottom up, which is only implemented by N hosts. Is not implemented by the network. Okay. And one of the key services that the transport layer is providing, if you remember, it's multiplexing and demultiplexing connections on the same machines, between the processes on the same machines, right? So the network layer doesn't differentiate between processes. The network layer addresses only machines, only N hosts. So network layer is going to take a packet and send it to another N host whose address is in the packet header as destination address. But once the packet gets to that N host, it needs to be delivered to a particular process, to a particular application to being processed. And the way you differentiate between these different processes is using port numbers. So the transport layer is the one who uses port numbers to demultiplex a packet when it arrives of an N host and deliver it to the proper process. Okay. And as if you remember, in the internet as a transport layer, we have two protocols, UDP and TCP. User datagram protocol and transport control protocol. And the UDP doesn't do much more besides multiplexing and demultiplexing of packets from and to processes. So we are not going to talk more about that. Now, the transport control protocol, which is the one we are going to talk mostly in this lecture, is providing two additional services: flow control, and we talk a little bit at the end of the last lecture, but I'm going to take to start again talking about it. We have more time during this lecture, and it's a very important topic. And congestion control. And the difference between the two is that the flow control, the goal of the flow control is to not overflow the receiver, a slower receiver. The congestion control is to not overflow the network. Overflowing means that the sender sends more data than the receiver or the network can handle. So during this lecture, we are going to talk about flow control and congestion control. Any questions? Okay, so again, from the last lecture and from many lectures ago, if you remember, this producer consumer is a bounded buffer. Bounded buffer meaning that it can accept only a finite set of items in the buffer. So this implements a natural form of flow control, because if the consumer cannot consume as fast as the producer sends the data into the buffer, inserts item into the buffer will get filled, and when the buffer is full, the producer can no longer add new items in the buffer. So the producer has to stop. So it's going to slow down over time to match the speed at which the consumer can read the data from the buffer. Right? Make sense? So that's pretty much, it now. So obviously the one problem you have with this one, and we are going to discuss more about it, is that if producer and consumer and the buffer are on a single machine, things are easy. But here, the producer and consumers are on different machines. So how do you know producer being on one machine? How does it know that the buffer on the consumer side is full? Right? So it needs to somehow wait for some acknowledgement from the consumer that it's okay to send more data. The simplest version of that is called stop and wait, and it's as simple as you can think of. We are going to use a lot of this kind of diagram, and you see you have sender and the receiver on both sides, and then the time goes down. Okay, so the oldest time is at the top, the newest time it's at the bottom. So stop and wait is very simple. You send a packet and you wait for an acknowledgement, and only after you got the acknowledgement, you send another packet. Okay. Now there are several important aspects, metrics here. So this is D, which is a delay or one-way delay, how long it takes a packet to get to the receiver from the sender, right? And this is, it takes some time, there are different overheads in the network. And on top of that, obviously, there is the speed of light. Okay. So across the continent, I think is what, maybe 10, 20 milliseconds in US, something like that. And now you need to wait for acknowledgement. So acknowledgement, it might take the same amount of time, assuming that is symmetric, the path is symmetric. It's not necessary for the path to be symmetric, because the packet from the sender to the receiver can go on a different path from the sender to from the receiver to the sender. And even if they go on the same path, there can be different level of congestion in the network. For instance, at a given time in the day, it's not taking you the same time to go from Oakland to San Jose as to go from San Jose to Oakland, right? Different level of congestion. But anyway, for simplicity, assume that you have the same one-way latency, as this assume no congestion. So if there are no congestions, it does take the same amount of time. And now, but then you need to wait for 2 times D in the best case scenario to get the acknowledgement back. And this 2 times D is round trip time. It's called round trip time. The round trip time is how long it takes a packet to travel from sender to receiver and back. Okay. So now, what is the throughput? How many packets you can send? So let's say, let me give you some numbers. So say that one-way latency, it's 1 milliseconds. Okay. Using this protocol, assuming that everything is symmetric, all the one-way latencies are the same for all packets, how many packets I can send in 1 second? So one-way latency is 1 millisecond. And I am asking you how many packets I can send in 1 second. Okay. 500. That's correct, Simon. Indeed, that's the correct answer. And it's very simple, right? It's like we can send only 1 packet per round trip time, because you need to wait for the acknowledgement before you send another packet. So the round trip time is twice the one-way delay latency is 2 milliseconds. So 1 second over 2 milliseconds, it's 1,000 milliseconds over 2 is 500. Okay, good. Sounds good. Okay. So how fast can you send data? You answer that question. Again, the little law applies on this case as a number of packets. It's B, how many packets you have in the system, times the round trip time, and B will be the number of packets you have in the system. Sorry, the number of packets you have in the system, it's only one packet, right? So you have one packet per RTT, right? Like we discussed, okay? Now, let's do a little bit more complicated here. Now you have, in this particular case, you have what is the throughput in terms of the number of bytes, not in the number of packets, like I mentioned. I asked you a little bit earlier. So if you have the round trip time of 100 milliseconds, so one-way latency is 50 milliseconds, and the packet has 1,500 bytes, that what is the throughput in terms of bits per second? So it's very simple, right? You can send one packet, means 1,500 times 8 bits in 0.1 seconds. So it's 120 kilobits per second. Okay. So the main point here, though, is that, as you can see, this is very simple protocol. You can implement it right away. So it's the advantage of this protocol. It's simplicity. On the other hand, it's very inefficient. You see, it's taking you cannot send more than at 120 kilobits per second, no matter how fast the network is. Because in this case, the throughput is governed only by the one-way latency. And the one-way latency will not depend, in most cases, if you think about it's mostly speed of light, it will not depend if there's a speed of light component of the latency of how fast is the network, how fast is the link. So if you have 100 megabits per second or 1 gigabits per second link or 10 gigabits per second link, you can still only send at 120 kilobits per second. So how can you send more? How would you modify this protocol to send more data? Batch acknowledgements. So if you batch, it's true. So, but if you batch the acknowledgement, this means that you have to send a packet before you receive the acknowledgement for that packet. Your intuition is correct, but of course, as you'll see, and that's a big part of the solution. But as you'll see, things will not be as easy. It's exactly Simon and Alison. Yeah, it's the same. You don't need to get block on ACK, because if you get block on ACK, then it's no longer you can send packets, right? But the problem is the following. Okay, you don't draw. It's your intuition. It's absolutely correct. The main problem here is that I need to wait for an acknowledgement from the previous packet before I can send the next packet. And the solution is, okay, don't wait for that, right? Send more packets. That's the problem. And if we wouldn't have losses, that will be great. But if the packets are lost, then here the acknowledgement serves two purposes. One, to slow you down, to slow the sender down, right? To block the sender. But the other one is also to say that the packet has been successfully received. So let's talk about losses. So in the internet, you are going to have losses like we discussed last time, right? And actually TCP, Transport Control Protocol, is going also to provide reliability besides flow control and congestion control. Right? But as a network layer, you are going to have losses because many reasons. It's like we discussed in the past. We have, your microwave can corrupt your wireless link. Even in optical networks, the bits can be corrupted. The wire can be bad, not very well connected, and many reasons. Or like we will see, the buffers in the routers are going to overflow and you are going to drop packets. Okay. So now when you with the packet you have associated basically as you'll see, so there are two ways to lose a packet here. First of all, the packet doesn't get to the destination at all. It's lost. The second one, the packet is corrupted. So you get the packet, but some bits are flipped. Okay. So on the receiver side, you need to know that you need to make sure that you get all the packets. The packets you got are not corrupted. And by the way, you also want to make sure that you get each packet exactly once delivered to the application. Okay. So this acknowledgement, like we saw earlier on, they also serve as an acknowledgement that the packet was delivered to the destination. Okay. So basically, if I am the receiver, I get the packet, I check the packet whether it's correct. How do I check the packet that is correct? They have the correct information. How you do it? Say you are the designer. Oh, yeah, that's yeah, you do have a checksum. Like a checksum, like parity bit is something more sophisticated than that, but that's the idea, right? So the packet has a data and has a checksum, right? So you take the data and you recompute the checksum using the same algorithms, and you compare that the computed checksum is the same as the checksum in the packet. If they are the same, you say this packet, the data is correct. Otherwise, you drop the packet. Right. Now, if a packet is dropped, like in our previous case, right? The question is that I'm sending a packet. The packet is lost, for instance. Or it gets a packet, it gets to the destination, is dropped. What I'm going to do? So what I'm going to do, because I'm going to wait indefinitely, because I'm going to wait for an act which will never come. So what you do here is basically very simple solution. Basically, you wait for a timeout. It's like you in real life. You are waiting for your friend to call, and he doesn't call at when it was the time you expected. What do? After a while, you are calling your friend, right? Or you go to meet someone and that person doesn't show up. What do? You wait for a while and then you leave, right? So now obviously, it's like, it's very important to notice here, by the way, that if you don't get the acknowledgement, it doesn't mean that the receiver didn't give the original message. No, right? Can you give me an example in which the receiver, I didn't hear about the acknowledgement, but the receiver got the packet and the packet is correct? So I send you the packet. I don't hear from you back. Yes, the acknowledgement is lost. The acknowledgement is also a packet that can be lost as well, right? So basically, you may send the packet, you may resend the packet because you don't get the acknowledgement on the timeout. And now the receiver gets a duplicate of the packet. So that's why the receiver has to have a way also to differentiate between a duplicate and the original packet. Because if the original packet was already delivered to the destination, to the process, you need to drop the duplicate, right? Okay, so this is the example when the ACK is lost, you resend the packet and now the receiver gets 2 packets, right? Now, it's one of the challenge here. It's how you are going to pick the timeout. If the timeout is short, you may get lots of duplicates. So why is that? Right? Remember that this, like in our simple examples, we assume that the one-way latency is constant. It's like in real life. It's like on the highway, like we discussed. The latency is not going to be the same. So you are too trigger happy with the timeout, and to resend the packet, I wait just for the timeout, the minimal timeout, right? That sort of the minimum round trip time. Then if I send, I may send too early because I didn't give enough time to the packet to make to the destination and the acknowledgement to come back. Obviously, if it was too long, then the performance suffers. So for instance, the round trip time, say it's 100 milliseconds and the timeout is 1 second, right? So this means that if there is a timeout, I lost the opportunity to send another 9 packets, right? Or 10, depends how you count. So how you deal with the application? Basically, you have somehow to put some sequence number in the packets, and these sequence numbers are unique, and the acknowledgement will be for a particular sequence number, right? And the sender, when you send, you keep the packets which are not acknowledged, right? So you know about, you still have the packets if they are lost. If a packet is acknowledged, the sender can can remove that packet from his buffer. And on the receiver side, I also keep a track of the sequence numbers of the packets I got. So if I get a packet with a duplicate sequence number, I can drop it. Okay. Of course, you want to simplify it by having only one message at a time. Again, and you just don't move until the message has been received by the sender, by the receiver. Okay, and this is exactly what we are talking about in our example. The problem, obviously, is that is slow and bad performance. So now, let's go back to solve our problem. And our problem was that how we are going to improve the throughput over stop and wait, right? We said that, in order to improve the throughput is quite easy, is basically don't wait, send packets without waiting for the acknowledgements. And we saw that doing that won't be that easy because the acknowledgement also acknowledge whether the packet was received or not. And if the packets are lost, things get complicated, right? But this being said, this is a solution, right, for improving the performance, right? You send a lot of packets without waiting for the acknowledgement. So we pipeline the sending, right? So that's very simple. Now, if you have this one, the natural way to implement this and to implement this protocol is to have what is called a window. A window is how many packets or how many bytes you can send without hearing for an acknowledgement. So if the window size, let's think about in terms of packets, then we think in terms of bytes. If a window size is 10 packets, this means that I can send 10 packets before I hear I get back the acknowledgement from the first packet I sent. Okay. So now in a round trip time, I can send a window worth of packets, right? Because this is how many packets I can send without hearing for an acknowledgement. Right, so therefore, in the number of packets which are in flight are going to be without, meaning in flight, from packets which are in flight, I haven't heard an acknowledgement for this packet yet, is a window size over the packet size, right? How long does the sender need to send packets around? Well, what is your answer? How many packets does the sender needs to keep around? So if the packets are lost, can still fix the loss. Yes, Alison, this is good. So you need to keep at least a number of packets which is equal with the window size. How long does the receiver have to keep the packet data? Remember, the receiver needs to keep the long packet data, or at least their sequence number, in order to avoid duplicates. Until the packet in the window is timeout. Let's forget about the protocol. When can you remove a packet? Think about your receiver packet. When can you remove the information about that packet? Again, the main reason you are going to keep that information around is to avoid duplicates. So I send you a packet. When do you know that I am not going to send you again that packet? When I send the next packet, depends on the protocol, right? With the next sequence number. It's a little more complicated than that. I think we are close. But fundamentally, the answer to my question is that you know that you can remove the packet when I know that you got the packet. Once I know that you got the packet, I'm no longer going to send you the packet again. And we'll see a little bit how that is done. It's not that easy. But yes, because you see, if I'm getting you the packet with the next sequence number, it's not necessarily the case, right? Because like here, if you look in this in this figure, a packet will be lost. If a packet, the third packet is lost, right? And I get the next packet. Actually, in some cases, you cannot remove the packet 1 or 2. Because in some protocols, the sender is going to start from the beginning to send all the packets. Okay, actually in TCP, in most versions of TCP, this will happen. What if the sender is sending packets faster than the receiver can process the data? In this case, it's quite simple. You slow down the acknowledgements, right? If you cannot get more packets, you slow down. Okay, so now we are going to talk about, these are some good questions and to keep in mind and see how they are solved. In particular, the last one. How long does the receiver have to keep the packets data? What if the sender is sending packets faster than the receiver can process the data, which is it's exactly the flow control. So now the TCP, again, I mentioned that last time, but it was very quickly, has a slide the window protocol at the byte, not packet level. So far we talk about packets, it was easier to visualize. And it has 2 ways to recover. Go back and is that if I miss some packets, right? I'm going to go back and I'm going to send the packets from the one which I missed and also the subsequent packets, whether you receive them or not. Selective repeat, you only send all the packets. It's called TCP SAC. You only send only the packets which are lost or the bytes which are lost. And the key way, the main way this TCP implements the flow control is by the receiver telling the sender how many more bytes it can receive. And this is called advertised window. And the acknowledgement contains the sequence number and of the next byte the receiver expects. So this means that the receiver has received all bytes in sequence up to and including n-1. If there is a gap, I receive the first 100 bytes. And then there is a gap of 50 bytes. And then I receive the bytes from 150 to 150. As a receiver, I'm still going to send to the sender 101, which is the next byte in sequence I am expecting. So next, we are going to go through a bunch of definitions about some variables. There are 6 of them. And then we are going to take an example, a simple example. So hopefully the examples will clarify things, okay? But, you know, it's, please, you know, bear with me. So this is a bounding, you know, if I'm taking this bounding buffer example, like I showed you earlier on in the lecture, and I try to map it on 2 hosts, sender and the receiver, this is one I can do it. I can have a buffer on the receiving process, that's a bounding buffer, and the sending is going to send into, you know, and these packets are going to be enqueued in that buffer, and then delivered to the receiving process. However, like I mentioned to you, like we discussed last time, this is not going to work well in practice, because this means that for each packet the sender process sends, you need to have a context switching, because the operating system is going to be involved in the act of sending the packet, because the TCP IP, the network stack, is implemented in the operating system. And if you do a context switching on sending every packet, like for instance, in the case of the internet, the packet size is typically 1500 bytes. Then in order to sustain the throughput of a 1 gigabit per second or 1 gigabit per second link, you need to send a packet every 12 to 12 microseconds. And if the packet is smaller, like 100 bytes, in less than 1 microsecond. And this is too little for the context switching, right? So therefore, how you solve the problem? You have other buffers. So in general, you have one buffer on the sender side and one buffer on the receiver side. This is what operating system maintains. And the processes themselves, can have other buffers, right? So actually, the process of sending from one process to another has 3 steps. The sending process sends the data to the operating system, or is buffered in the TCP layer. The operating system is using the IP layer to chop the data you send from the sender into packets and send it to the receiver operating system. The receiver operating system will put the data it receives in a buffer. And then from this buffer is going to deliver the data to the receiving process. Okay. And by the way, the fact, you see, that I have a buffer allows me for something else. The sending process can have a stream-oriented protocol like we learned. So I can send a stream of bytes, 1000 bytes, 4 kilobytes, whatever. And then the operating system, this buffer, I put all this data into the buffer, and the operating system can then take the data and chop it in packets, because that IP layer is not a streaming protocol. You have to send packets. I need to take some piece of data. I'm putting the headers, port numbers for a source and destination, IP addresses. Then at the lower level, you put the MAC addresses and things like that. Okay. So now, let's assume that the maximum IP packet size for this example is 100 bytes. Again, in general, in practice, it's 1500 bytes. In the size of the receiving buffer is 300 bytes. So the receiver this is a buffer, 300 bytes. Also recall that the acknowledgement indicates the next expected byte in sequence, not the last received bytes. And like we discussed last time, we use circular buffers, right? If you remember. Right? So basically a circular buffer is like you see here, is basically goes around, and you keep the head and the tail of the buffer. Okay, so now with all of this, let's see how things are working. Like I mentioned, we are going to decide to define 6 variables. Last byte written. So this is the sequence of the last byte written by the sending process into the operating system buffer. Last byte sent is the last byte sent by the sender to the receiver. Last byte act is the last act received by sender from the receiver. Last byte received is the last byte received by receiver from the sender. And next byte expected is the last in sequence byte expected by the receiver. Is it a convention to start circular buffer at 1 index? It depends what language you are going to use. If you use C, it's probably 0. Yeah. Okay. So now let's take the examples. And sorry, the last byte read is the last byte read by the receiving process. Okay. So this basically says that you have in this blue area in the receiving buffer is how many bytes you have in the buffer, in the receiving buffer. you consume from one end. So this is the start. The last byte read is the start of the buffer, of the data in the buffer. Last byte received is the last byte in this data of the data in the buffer. And next byte expected in this case is the last byte received plus one, because that's the one you expect. Okay. So now the advertised window is by definition again, how many bytes the receiver, the sender can send me without me overflowing. So basically, if I'm the receiver and my buffer size is 300 bytes and the buffer is empty, I tell you, you can send me 300 bytes. If my buffer, I already have 100 bytes worth of data in the buffer, I tell you, well, you can send me only 200 bytes. So this formula is computing exactly what I told you. It's a max receiver buffer minus how much data I have in this contiguous region in the buffer, which is last byte received minus last byte read. Okay. The same, in the same thing, it's in the, on the sending side, or similarly, right? Here I have last byte act. So here, if I get an acknowledgement in this protocol, if I'm going to get an acknowledgement for a byte, this means that the receiving process receives that byte. So I no longer need to keep it in the buffer as a sender, right? So everything before last byte act can be dropped. And then you have last byte sent. So what is last byte act? What is these things between last byte act and last byte sent? This green area. This is green area represents the data that the sending process send it without being acknowledged. That's it. Okay. So let me see. It's exactly, Simon. Yeah. The packets we send that have not received an ACK, so they are not acknowledged. So now think about sender window. And this again, you have the formula, you can look at the formula, but let's take an example. Now let's think about from the sender perspective. Say the receiver, you are the sender. The receiver tells you, my advertised window is 300 bytes. And since I learned this information, I already send you 100 bytes. How many more bytes can I send you before I'm hearing back from you? So that I am absolutely certain I'm not going to overflow you. Right? So it's again, the receiver tells you, you can send me 300 bytes. Since you heard that, then when you heard that, you send 100 bytes. Still nothing from the receiver. How many more bytes you can send before you hear from the receiver? Yes, it's in my example was 200, right? Right? Receiver told you, you can send me 300 bytes, you send 100 bytes, you haven't heard yet, you can send another 200 bytes. So then you send in total 300 bytes before you hear back. You cannot send more. And this is exactly this next formula. The sender window is how many more bytes you can send without overflowing the receiver. And it's advertised window minus the number of bytes you send out without being acknowledged in that window. Okay. It's still true. This is a very important aspect. This is still true if you miss the data, these formulas, right? Because if you miss the data here on the receiver side, the next byte expected, by the way, you see here, the next byte expected is the one which is in sequence, right? Because you have a gap, the gap doesn't matter for the next byte expected, but for the last byte received, it matters. Okay. So remember that. So these are the same formulas if you miss the data in the middle. Okay, so now let's take a simple example. So let's say the sending application sends 350 bytes. We assume the IP only accepts packets no larger than 100 bytes. And let's say the max receives the advertised window, max receiving buffer is 300 bytes, and advertised window initially is 300 bytes. So sender first, send first packet. How much big is the first packet? 100 bytes, because that's the maximum size of the packet. With green, I show the packet which are sent without being acknowledged. Here on each side, I'm saying 1 to 100 between these square brackets is the bytes which are being sent. I am starting from 1. Okay. So eventually, the last byte sent when I'm sending initially the last byte act, it's 0. Nothing was act. The last byte sent is 100 because I send 100 bytes. And now eventually this packet is delivered to the destination. Last byte receives, it's 100. Next byte expected, it's 101, right? Everything is good. Now, the receiver sends back acknowledgement 101, advertised window noise 200, right? Because it was 300, I got 100, now you can send me only 200. Okay. Before receiving this acknowledgement, because the window, advertised window is 300 bytes and I send only 100 bytes, I'm going to send the next packet, me being the sender. The bytes are between 101 and 200, right? And again, sorry, here I am saying all the packets which are being sent, all the bytes which have been sent. So now I send from the sender between 1 and 200. Okay, this packet is going to, now the last byte sent is 200, and it's going to get to the receiver. And the receiver, you have last byte received 200, next byte expected 201, and I'm going to now write 201. Now, assume that next thing's what happened. The receiving process reads some data. Let's say it reads 100 bytes, the first 100 bytes. So now in the receiving window, in the receiving buffer, I only have 100 bytes because 100 bytes already were processed by the receiver, were already delivered to the receiver process. So when I'm going to send back an acknowledgement, I'm going to include the next sequence, next byte expected, which is 201. And then advertising window, it's again 200. Because in the buffer, I have only 100 bytes, and the buffer is 300 bytes. Now, the sender, it's again, I still have, I know that I send only 200 bytes. The receiver told me initially that I can send 300 bytes. So I still can send 100 bytes. So let me send the next packet. But let's assume now, to make things more interesting, that this packet has been lost. Okay, that's fine. In the meantime, I advance the last byte set sent as on the sender to 300, and in the meantime, and the sending window now is 0. I can no longer send. You see, the sending window magically now is 0 because I sent 300 bytes. I knew that the advertised window is 300 bytes. I haven't heard anything from the receiver, so therefore I have to stop sending. Okay. Now, in the meantime, I get the first acknowledgement back. The first acknowledgement back is telling me I have 101, the acknowledgement 101, and advertised window is 200. Right? So the first packet was acknowledged. Right? So because the first packet was acknowledged, it was acknowledged, and also indicates the next packet to send. So the receiver no longer needs the first 100 bytes. So I'm going to remove this from the receiver from the sender buffer, because the receiver told me that it got the first 100 bytes. Okay. So, and I am going to advance last byte act 100. But the sender window is still 0 because, right? Because I sent 300 bytes. And now the sender told me, okay, I got 100 bytes, but I can receive only 200 bytes, 200 more bytes. So yes, okay, I removed the 100 bytes that sender sent told me that that the receiver told me that they received. But still I have 200 bytes which are not acknowledged. And the receiver told me that it can only receive 200 bytes without being acknowledged. So I cannot send anything. But finally, now I get the second acknowledgement. And the second acknowledgement tells the receiver that tells to the sender that the receiver got the first 200 bytes. So the next expected byte is 201. And the advertising window is 200. So now when you compute the advertised window, you get 100. Because it's 200 advertised window. And now I have in flight only 100 bytes. So I can send another 100 bytes. I don't have 100 bytes to send. I only have 50. Right? Because I wanted to send 350 bytes. So I'm going to send these 350 bytes, the last 50 bytes. And then they are going to be received by the receiver. But now I have a gap, and the gap is a third packet which was lost. So you see, now next byte expected is 201, right? And the last byte received now is 350. So now I send back to the receiver and say, look, I got the next byte I am expecting is 201, but the advertising window is 50. Okay. So if the advertising window is 50, what is the sending process going to do? Right? Yes, you can send in this case, you can send the packet which was lost. Why you can send this packet which was lost? We'll do more about this in a while. It's still in the green region. It's exact. but the sending window is less, yeah, it's good. But the sending window is less than 0. It's good. It's very good observation. But the point here that I can resend the packet because I already sent that packet. It doesn't count. I can always resend a packet which I previously sent, right? Because in the worst case, it will be the duplicate. In the best case, in the worst case, it will be duplicate. In the best case, it's going to repair a loss. You see? The receiver, by this gap, already accounted for the lost packet. That's a key. Right? So you see, it's already accounted. The next expected byte is 350. So therefore, if I'm going to send a packet, that's not going to change the window on anything. It's again, either it's going to repair a loss or it's going to be duplicate. So that's why I can send the packet. And why I'm going to send now, in this particular case, a particular case, I am going to send it because, you see, it's the second time I get acknowledgement. Sender, the receiver told me that the acknowledgement is the next sequence number it's expecting is 201. So basically, and we'll see this next. This is a way to detect a failure. Okay, so I can a packet loss. So one way to detect a packet loss is that if the receiver tells me multiple times, I am waiting for this sequence number, next sequence number, right? Because this means that the reason it's the receiver will tell me that it waits for the same sequence number over and over again is that I send him another packet, but it's a gap. It's not in sequence. Because if it's in sequence, the next sequence number the receiver will tell me will advance as well. Okay. So anyway, and now if you have if finally you get the next packet, the lost packet, the receiver gets the lost packet. Now he has everything. It's got up to 350. It's going, the acknowledgement will contain 351, which the next sequence number is going to wait for. Advertising window is still 50. And now when the sender gets acknowledgement 351, it can remove everything from its buffer because all the data is sent was acknowledged. So now we are done. Any questions? Yeah, so please, you should, you can go through this example. It's very revealing, but you need to go a few times to really feel it, understand it. So let's have a short discussion before we move. Yes, almost everything we talked goes to back end and selective repeat. The only difference is, like it was said, someone said, for instance, the difference here, this was mostly I shown you about selective acknowledgement. So I'm telling you what is the difference. So with go back end, the sender is going to send everything up from 2001, including the last 50 bytes, which are already received by the receiver. Okay, so you already go from the first sequence number, which was expected of the missing packet. Okay, in the case of selective acknowledgement, there is a sender is, like in this case, is going only to send out the missing packets, the missing information. Yes, would last byte read cause a bottleneck on how, this is a question from Simon. Would last byte read cause a bottleneck on how fast we can clear the buffer if we are not spending enough cycles to mem copy from buffer to process. We cannot advance last byte read as fast, so that limits our advertised window. Absolutely, and that exactly the purpose, the goal of having this last byte read. The goal is basically, yes, it's here. The ultimate receiver is a receiving process. So the receiving process, for some reason, cannot consume data, which the sender shouldn't send faster. Okay. Okay, so let's move on. Let's go. So why not have a huge buffer at the receiver? Memory is cheap after all. A huge buffer as a receiver also means a huge buffer as a sender, right? And we'll see that huge buffer actually also in the network for congestion control means that the latency is going to increase significantly, because the latency is going to increase significantly because it's going to take more to send to clear the buffer. Yeah, so it's large retransmission. The round trip time, the retransmission time is going to grow a lot. Sending window also depend on network congestion, is what I'm going to go on to do next. There are a lot of details about, if you are interested about networking, take CS168. And by the way, we talk about a few two buffers here in the operating systems for the sender and the receiver side. In practice, there are more buffers. There are network card has buffers, buffer in the network, and everything. So let's announcements. Midterm 3 is tomorrow. What we've done over today in the lecture is not is not included in the material for the exam, for the last midterm. On Sunday, we are going this project 3 party between 10 and 2 p.m. The discussions will be converted in office hours to help you with the projects, last project, and with the exam. If you have, well, it will be after the exam, so it don't help you as much. The office hours also will continue into that week, again, to help you with the projects. Homework 6 is due Friday. And next Friday, and project, no, yeah, this Friday, sorry, not next Friday. And the project 3, it's due, as you know, on December 8th. Okay, so now we have another 15 minutes. So let me tell you a little bit about the congestion control. So flow control, don't overflow the receiver. Congestion control, don't overflow the network. The network has routers, has buffers in between. So now the question is how you are going to detect the congestion in the network. And remember, the congestion I'm going to detect as a transport layer. There is no transport layer in the network. It's only between 2 end hosts. So I can only observe the network. There are a few ways to detect the congestions. One, a packet is dropped. You interpret this to be a sign of congestion because you assume that the reason a packet has been dropped is that because a buffer of the router was overflow. So filled in, the router can no longer, cannot send packets as fast as it gets. The buffer fills in, packets are dropped. There is a more refined version, early congestion notification. So when the buffer at the router increases over some threshold, the router set up a bit, it's called ECN bit, in the packet. And then the receiver sends back to the sender saying, hey, don't slow down because this router is about is congested. And the other one is delayed packets. When the buffer grows, the end-to-end latency grows. It's like on the highway. So if I see that the delay has increased, maybe I need to slow down. The simplest one, it's drop packets, and this is what we are going to assume, is still most used sign of congestion today. And like we discussed, there are two ways to detect these drop packets. Again, the question is, how do you detect a drop packet? Right? Congestion means the router buffer is full, and then because it's full, the packet is dropped. But now, if I'm the sender, how I'm going to know that the packet was dropped? How I'm going to decide the packet was dropped? One way is like we discussed earlier on, timeout. I wait for some time, which is significantly larger than the round trip time. I don't get an acknowledgement. I assume the packet is lost, even if it wasn't. So I resend it. And the other one I just alluded to you earlier on, it's when I received the same acknowledgements, the same sequence number in the acknowledgement, the next sequence number, expected sequence number, over and over again, right? Because again, in this case, I'm going to send you, so in this case, I send you the packet, 200, right? From 100 to 200. So you tell me, oh, the next sequence number I am expecting from you is 201. Now I'm sending you the next packet with the bytes 200 to 300. You lost it. You don't tell me anything. Now I'm sending the next packet 300 to 400. You give me the acknowledgement for that packet, but if the sequence number, next sequence, expected sequence number is still to 100, because you are telling me about the in sequence, next expected in sequence number. So now you told me 2 times 200, the next sequence in sequence number you expect is 201. I'm sending you another packet now between 400 and 500 bytes. Again, you tell me the next byte in sequence I'm expecting is 201. So again, an acknowledgement, which is duplicate. This is what we call duplicate acknowledgement, because you tell me repeatedly over and over again. You told me over and over again, the next sequence number I'm expecting is 201. So after a few of those, I decide, well, that packet was lost and I'm going to resend it. This is duplicate acknowledgement. Make sense? So congestion control, the key idea is a sender to increase the sending rate if the network, until congestion, if the network is not congested, and reduce the sending rate if the network is congested. How does the sender control sending rate? Sender window size, the sending window size, which is called right now in this context congestion window size. Here is a great question from Alison about the previous case, what I mentioned to you. So the question from Alison is the following. Can you not conclude it was lost, the packet was lost after the first duplicate act? Tell me why you wouldn't do that. You could do that, but why you wouldn't do it? Maybe out of order. Yes, it's exactly out of order arrivals. You see, look at this figure and assume that these packets, which is lost, instead of being lost, it travels on a different path in the network and arrives actually at the destination after the packet, the force packet, the one which, right, after that, after the last packet, right, which was sent by the sender. So the sent packet is lost in this example, but assume it's not lost, but it arrives after the force packet. So if that's the case, the sender will see the same things. It cannot differentiate between the two. So waiting for more duplicate acknowledgements, it's a way to make it more sure that the packet was really lost. And it's not because the packets are reordered. And the packets are reordered because every packet can take a different route in the network. Which means also is true, Taiwo, that three duplicate acknowledgement, missing a three duplicate acknowledgement does not necessarily always guarantee a packet has been lost. It's correct. It just increases the probability that assertion to be correct. Okay? So how does the sender control sending rate? It's using again a window. It's called congestion window size. And congestion window size it's going to take the minimum between the sending window size and this congestion window size, which is computed in the network. And obviously it might be less than the receiver advertised window. And increase the size of the window then until congestion, and reduce the size of the window if congestion, right? Because the window size, it tells me how many packets, how many bytes I can send without being acknowledged, right? So bigger window means higher throughput. I can send more data before being acknowledged. Smaller window size, I can send, if it's one packet, I can it's stop and wait. So finally, let me tell you, I'm going to spend a few minutes on this plot. And this is just to give you a taste about how the TCP is working and congestion control is working. This is right. So first of all, I don't know how much, when I'm starting to send data, as a receiver, as a sender, I know, how much the receiver can handle, because the receiver, there is initially when I establish the connection and a three-way handshake protocol, and the receiver tell me about the advertised window. It's advertised window. So I know that. I know how much to send without overflowing the receiver. But I don't know about how much I can send without overflowing the network. So there, what I'm sending, I'm going to start with a congestion window of 1. Let's again think about now congestion window 1 packet to simplify the discussion. So I'm moving from window measuring in bytes into packets, to packets again. So I'm sending 1 packet and I'm waiting for acknowledgement. So I'm sending only 1 packet. So it's like stop and wait. But now when I'm getting the first acknowledgement, I say, oh, I sent a packet, it went through. Let me be more aggressive now. So I'm going to increase the congestion window when I get the acknowledgement by 1. So now I'm going to send 2 packets. And each acknowledgement I get, I mean, add another one to the congestion window. Now, this is called slow start. Slow start is a terrible name because actually, if you think about in the slow start by using by CW is a congestion window here. If you increase the congestion window every time you get a knock by 1, you double the congestion window every round trip time. In the first round trip time, I send 1 packet, I got 1 acknowledgement. So now in the second round trip time, I send 2 packets. I get 2 acknowledgements. For each acknowledgement I get in the second round trip time, I'm going to increase the window size by 1. So from 2 is going to go to 4. Now in the third congestion window, round trip time, I'm going to send 4 packets. For each acknowledgement, I'm going to increase the congestion window by 1. So I'm going to have 8, right? So this is what you see. The congestion window size is on the vertical. So it's going from small, double every time. And at some point, I am going probably to lose a packet because I sent too much. This is when the packet is lost. So what I'm going to do when that happened? You need to be very aggressive, because it turns out that if you are not very aggressive, and this is, it's a queuing theory property, we don't have time to go into it. But if you don't reduce the sending rate very fast, you cannot relieve the congestion, right? So in this case, okay, you are very dramatic. So you are going to go with the congestion window all the way to 1, reduce it. And then you go again, slow start, again, exponential increase. But now you go through until to this threshold. And this threshold is a congestion window. In the previous slow start, you are still successful. All the packets made it, right? So congestion window, it was 8. I sent 8 packets. I got 8 acknowledgement. Then when I congestion window increased to 16, I lost packets. I'm going the next time. I'm only going to stop this slow start or aggressive start to 8, because I know that kind of was successful last time. And then I'm going to be much more timidly explore, how increase and explore the capacity of the network, right? So I'm going to increase now with 1. I'm going only to increase, this is what I was talking about. And now I'm going to increase only the congestion window by 1 per round trip time. So this means that now, when I'm going to get an acknowledgement, I'm going to increase the congestion window by 1 over n, where n is a current congestion window size, right? So if I have the congestion window size is 10, and every acknowledgement, I'm going to increase the window size by 1 over 10. Now, in 1 round trip time, I'm going to increase the congestion from 10 to 11. So you get this one. So this is additive increase. It's called additive increase, right? And then I get a loss here. If I lost here, maybe it's because 3 duplicate acknowledgement. Now I'm going back. If it's 3 duplicate acknowledgement, I'm going to get back to the threshold, right? And then I grow again and things like that. Okay. So, so that's basically what it is. So there is a early stage in which you grow very fast to explore the limits of the network. And then after that, you get into this regime, which is at the end, you additively increase then the window size, and you get a loss, you multiplicatively decrease. This is called multiplicative decrease. Basically, you cut it to half in general. You grow linearly, you cut it to half. You grow linearly, you cut it to half. So that's pretty much it. It's fascinating algorithm. It's very, very simple, but in dynamics, the dynamics are fascinating. So I'm going to stop here, and we talk about the networking summary. We talk about network. We talk about networking. We have a few lectures on that. Remember, the internet has 5 layers: physical layer, data link layer, network layer, transport layer, application layer. And we talk about end-to-end argument. End-to-end argument is saying that if higher layers can implement functionality correctly, you should implement the functionality as a lower layer only if it improves the performance significantly for applications that need that functionality, and it does not impose burden on applications that do not require this functionality. And we discuss flow control, whose goal is not overflow the receiver buffer, and congestion control is the main goal is to not overflow the network. Thank you. And next lecture I'm going to do, it's a special topics. I'm going to tell you a little bit about some of the research which we have been doing at RISE Lab and AMP Lab. Okay, see you all. So I'm going to stop here, and there is a question I'm going to take.